Either they told you what you should be, or they gave you something that did not fit directly into any of our rules. That's interesting. So they give you 21 also, or is that just an example? Number 21, why on earth did they say to let u equal x over 3? I thought there was an arctangent rule for that. Whatever. You were supposed to follow what they said. So what would happen if u was x over 3? Where would you guys go from there? Du. Some of you might have gotten there quickly. Some of you guys might have gotten there in a longer fashion using the quotient rule. But either way, yeah. How would you have substituted them? Factoring out a 9. Factoring out a 9. Eventually a 1 over 9, but factoring out a 9. I can't factor out it. You can factor out whatever you want. Just whenever you factor, what do you, like I'm showing my algebra kids, whenever you factor, what do you have to do? Divide. So you're going to have a plus 1. That's easy. What's not easy? Well, you're going to have an x squared over 9. What's x squared over 9? Isn't that x over 3 squared? X over 3 times x over 3. So this could become a 1/9 times dx all over x over 3 squared plus 1. Guys, what's the tangent inverse of u derivative rule? Yeah, 1 over 1 plus u squared times u prime. Do you have a 1 over 1 plus u squared or u squared plus 1 right now? Yes. Are there technically two different rules for tangent inverse with derivatives and integrals? No. Just the whole A thing is to make this type of problem a lot easier. Because otherwise you'd have to make this mental jump of, oh, hey, make this a 1, and now I can figure out who my u squared plus 1 is. And it's kind of weird sometimes what that u might be. So this technically, well, I would need to get into my u squared plus 1. I would need to plug in my du is 3, right? Sorry, dx. So I would need that 3 over 9. My du, or 1 over times du, either way. And that gets me back to my 1/3 arc tan, or tangent inverse. It just looks like the cool u squared plus 1. Could we do that every time? Yes, but what is a lot easier than factoring something out to make a 1, which sometimes makes the variable expression nasty? Yeah, just memorizing the other variation with a u squared plus a squared, where we can kind of avoid all that work and get our 1 over a tangent inverse of u over a plus c. Anyway, I just thought it was an interesting problem because it's showing you how technically the derivative rule is there. We're just kind of memorizing a variation that avoids all that work for us. Okay, but number 49. Do you have a sine squared anywhere in your integration rules, including, for those of you, Dean and Gavin and anyone else just joining us, although I think everyone's here today. We were just talking about these, where were they? Here we go. These basic integration rules. Some people took pictures. We talked about which ones are tricky, specifically 10 through 13 and 18 through 20 are tricky to remember. Yes, they're in your forever cards, but this is a nice little compilation of all of them, minus the endeavors that we've talked about, or the endeavor, I should say, with like the integral of ln. Who's that? Okay, that's not on here. That's extra. That's kind of crazy. But is sine squared in any of those, even the nasty ones? No. So what was their thing? A double angle formula from pre-calculus. Why would they give us that? Oh. Why would they give us that? How do you guys use it? Can't you see 2 sine squared x is equal to? If I were you, I would have added it and subtracted it. 1 minus cosine of 2x. Oh my goodness, you can take a sine squared and make it a cosine 2x. Why? Well, 1 minus cosine 2x. Why would you do that? Okay, it's not that pointy. Yeah. Which one's easier to integrate? those trig rules, all those trig properties we had to memorize, they make impossible integrals possible. At this point, we would just have a what? X integral of cosine is sine, derivative of sine is a positive cosine. Anybody think through that when they're taking integrals? Uh-oh, but my u is 2x. My u prime would have been 2. Don't I need a 1/2 to offset? Pause. Do you have to do these mental math? No. Just make sure you're getting them right. So show the work, get it right. Mental math, get it right. And if you start getting it wrong, slow down. Show work. Remember, you can always double check by deriving. Derivative of x is 1. Derivative of sine of 2x times a half is cosine 2x times 2 with a negative plus. Dun, 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 dun. Okay. Are we ready to go grade? Some of you have odds that you might want us to look at. I'm going to ask for those in just a second if your group wasn't able to help you out. But for right now, here we go. Evens, wrong tab, lo siento. Good. Oh no, where'd it go? Oh, I closed it with the whole kid setting. Sorry. My YouTube is going into all this, like, I don't know, video audience stuff. I'll figure it out today. All right, chapter 7. Sorry, guys. Come on, be happy I closed stuff for you. Woo-hoo-hoo, look at this guy. Who's this guy? There's a U, there's a V, there's a DV, there's a DU, I think. Hey, guys, look at the Endeavor card on the wall. What's the next one? Here we go. Section 7.2. U's and DV's and D's and DU's and... Okay. Number 6, it was just asking if you know your basics, right? Integral of e to the x, integral of secant tangent is secant. Integral of x to the 1/2. You guys, your power rule. Can you do the basics? Number 18, there's a u sub. There's a u sub. All the way down here. Sorry, this is just a checking step to make sure you're right here. 1/4 sine is 2x squared plus c. Number 20. It's a u sub. You needed a 7. You could have separated 28 by mental math, or to be 4 times 7. The 7 gets lumped in with the du, and the 4 is left. Oh, wrong way. U is 7. The 4 is left. Oh, there's the 4. X minus 2 to the 4th power plus c. We would have had the 4, but the x to the n plus 1 over n plus 1 would have canceled it out. Number 70 is a bit of an adventure. They use log properties to help them out in order to use the quotient property to split it up. And then to go ahead and take the derivative to show why the integral of cotangent is ln of sine, or how I should say. There it is, it turned out. Hang in there. Wow, that's cool. And then I just plugged in the point to show the point works. They were showing this one works, they were showing this one works. They went ahead and took that original, took the derivative. Hey, it does, it is cotangent, it's cosine of sine. And then plug it in, just don't forget any log of 1 is 0, including ln. Oh, and that was it. I gave you guys mostly odds on purpose. So, where we get stuck in homework, if we got stuck in homework, I'm ready and I have it open, I think, section 7.2. Yeah. Do we have anything we want to see? Oh, we're okay, really? Okay, you go for section 7.3. Here we go. Something new. Euler's method. It was new. Euler's method. It was new. Integral of ln. Maybe we're supposed to memorize what's going on there. That's new. There's it. not so good at A to B, or to be honest, E to B with some of you. But these LN guys, who on earth are they, and where did they come from? And I wonder if this will tell us or answer all those questions for us. Integration by parts, section 7.3, and standard deliver was the tic-tac-toe method. That was on the board. And Angel was having his pity party. What was it? You guys all know I can't do calculus. You'll be better off without me. And Escalante was like, do you want me to do it for you? And he said yes. He's like, your answer should be no. Anyway, what was that? Tick, tack, toe. We did not learn it last year. And to be honest, it is only one special type of problem in this section, not the entire section. It's just one special trick for a certain type of problem that would need this process multiple repeated times. Now, so section 7.3 says integration by parts. Yes, it's new. Yes. However, you guys writing the intro part yet? What is the intro part saying? That don't need integration by parts? There are tricky integrals that don't need this new process. I'm trying to warn you that just because it looks different, just because it looks complicated, just because it doesn't look like a nice normal rule, doesn't mean you always use integration by parts. So to introduce like, hey, some integrals have been impossible for you to solve without this new procedure. To introduce that, I'm saying, but I think some of you would think that this is impossible to solve and it's really not. Or this is impossible to solve and it's really not. Or I think I have another one on the next page. So integration by parts, yes. It will make some, to us, impossible problems possible, but not all tricky integrals can or even need, or I should say need or even can, use this process. It's a very specific type of problem that fits in this category. So, first of all, I've given you a hint. This is a disguised form of a log rule. This does not need a new process. This is able to be solved in old-fashioned way. What would you guys do? If it's a log rule, well, I think the U is the bottom, right? If it's a log rule. Remember, log, arctangent, which way do we go? Okay, fine. So now what? Is equal to? 0 plus, right? So dx is equal to? And this would be? What do we do if we don't have what we need? What's e to the x equal? That's not our tangent. That's not log. That's pre-calculus. What topic in pre-calculus could go from a factored denominator to smaller fractions that are undoing the common denominator? Yep, you're saying it. Say it louder.
Yes. Partial fraction.
Remember the thumb rule trick? I had to use my palm. Oh. How we would cover one and say, hey, what's your 0? What's his 0? Oh dear. Nope, we're not ready for that. Just kidding. Remember how we would use A's and B's? Don't worry, we have a section coming where we're going to actually review this. And we would get rid of the denominators on both sides. Distributing the U cancels. I have A, U. I could just do A times U minus 1. Plus B times U. And this is technically a 0 U plus 1. So I could say the AU and the BU, the A plus B has to equal 0. And then the negative A, he's the only non-U dude. Okay, the negative A has to be 1. So then A is equal to negative 1. B then must equal 1. So I have negative 1 and 1. That works? Yep. I could have plugged in the 0. 0 minus 1 is negative 1. 1 over negative 1 is negative 1. I could have plugged in the 0 is 1. 1 over 1 is 1. There's a shortcut. Anyway, why does that make all the difference? Can I integrate this? It's just a log. How many of them? 2. And what are they going to be? Well, let me get rid of all this partial fraction stuff because I just showed you guys there was a shortcut. And I explained or at least referenced how we're going to actually review it when we talk about logistic questions in section 7.5, or logistic growth, I should say. We'll review partial fractions, but long story short, what's the integral of 1 over U, guys? So isn't this going to be negative ln of, who's U? Oh, 1 plus e to the x. Uh-oh, how am I going to do this guy? Oh, stink, I need to do v substitution. So v is equal to u minus 1. Pause. Mental math. If this is my u or my v, what's my dv? Just 1, right? Do I have the 1 that I need? Do I have the u prime that I need? Yeah. I can actually just go ahead and go straight to ln of u minus 1, which would be 1 plus e to the x minus 1, just e to the x, plus c. But you could write this multiple ways. You could just make this guy x. You could do a quotient property and do e to the x over 1 plus e to the x. You cannot split that guy up. Anyway, different ways of writing it, but long story short, is there technically a way to solve this without any new information? Yeah, but what's new to us in calculus? Partial fractions. So we have to talk about that. We will in another section. I'm just saying there are tricky ones out there that we can technically do. We might just need to review Okay, moving on. But what about this guy? This guy's impossible, right? Getting you ready for the test and getting you ready for the AP. Is this meeting this new process? If I'm saying no, if I'm saying it's a disguised power rule, there has to be a u. What are your options? This guy? du is cosine. I hope not. This whole guy? du would be, okay, wait, if u is ln of sine, what's the integral of ln of sine? 1 over sine times sine prime. Cosine. Oh, that's cotangent. Do I have my u prime with my u? Yep. It's just hard to see. Don't you dare go moving stuff. It's illegal. That squared is outside the ln, not inside the ln. stuck and I'm done. Okay. What were those two problems meant to kind of do? Humble you a little bit that even if you totally rocked section 7.2, harder things are coming. But this section is not meant to be like, hey, let's rock every single possible harder integral that's to come. No. This section says, let's give you a very specific type of category, and don't worry, I don't think they might give a few tricky ones at the beginning just to kind of humble you some more. But then they'll say something like solve by integration by parts. We're teaching you how to use this new technique so that hopefully at the end of this chapter on the AP, when you have just lots of different random integrals thrown at you, you can categorize and say, hey, that's a good integration by parts one. These two are not them, but other ones are. So let's get a feeling for who this guy is. No, I didn't want that. Who this guy is. There we go. Oh, I have some more tricky ones. And we'll save those for another day. It's a chapel day. We don't have tons of time. We'll do a couple of tricky ones in the beginning, maybe of our notes tomorrow. I have plenty of tricky ones, but let's just get into, okay, so wait. This is for a very specific category of problem. What is that category? Write this guy down because he's a great intro problem. When is parts necessary? When is parts necessary? Well, here's one. Almost always, if you see any sort of polynomial, a linear, a quadratic, a cubic, with a trig, not a trig inside, but a trig multiplied, it's almost always integration by parts. Now, has anybody even thought about if you were to try u sub, who you would do? If u was x, what would your u prime be? 1 doesn't help us with sine. If u was sine of x, who would your u prime be? Cosine. Doesn't help us with the x. Whether you make the u this piece or the that piece, you're like, it doesn't help me with the other because we have to think about them separately. Let me show you one. Particle. Good old-fashioned particle derivative. We know there is no such thing as a product rule for integration. Okay, product rule. How does it work? I have a u, I have a v, I have a box, I have a triangle. We do second d first. Technically, they do it always in a backwards order. That's fine. Second d first, so v times u prime, or du dx, plus first d second, which would be, okay, u and v prime. So you could think of, right, box triangle prime plus triangle box prime. Either way, product rule. Yeah, it's a thing. This is a weird way of showing it. We like F's and G's maybe, but whatever. Sure, product rule. What can we do with product? What if we were to multiply everything by dx? What if we were to multiply everything by dx? How could we rewrite this? Okay, so if I was to multiply the whole shebang by dx. We've done some of that before. We've had like a dy dx. We've multiplied dy dx on the other side, separation of variables. We've kind of done this before. Okay, what would end up happening? So, on this side, wouldn't we have u dv, you guys agree? Plus v du. Still good? And then what would be over here? dd. How does that make sense? Maybe there's an easier way of thinking about it. What if, okay, we're going to get back to that. You don't necessarily have to erase it, but what if we were to try to integrate both sides? What if we were to try to integrate both sides? Yeah? Maybe I should show you why we're multiplying by dx. we could go ahead and then integrate. Well, wait a minute. This one's integrating a derivative, right? What happens when we integrate a derivative? They're inverses of each other, inverse operations, right? This one says take the derivative, this one says go back. Okay, aren't we going to get to uv again? Does that make sense? The derivative of uv integrated will be uv. Okay. So kind of using FTC just a little bit, but without bounds. But on this side, well, wait a minute. This side we're having some issues just a little bit because we're going to have our u dv dx plus, we can separate our integral, our v du dx. Do you see why I had you multiply dx? Can we take an integral right now with u and dv dx? Or do we always have to separate? So if we were to separate, I'm going to go ahead and just for 1 second more, I'm going to keep this written. You guys have the idea of what we need. I'm just going to keep it unsimplified for one more moment. Now let's go ahead and multiply both sides by dx. The idea is separation of variables. I said it, but I didn't show it, and I regretted it, so I then went ahead and went backwards a step. So now we have the integral of the derivative of uv. We have the integral of u dv. We have the integral of v du. We were ultimately separating our variables in essence to kind of get down to that differential notation that we're used to, but some of you are realizing we have u's, we have v's, we have that u's derivative du, we have that v's derivative dv. We've gotten rid of the dx here, so we can still use that idea of the inverse operation of differentia and integration, derivatives and integrals. We have our uv. Okay, so here's what we have. Kind of moving backwards from the product rule, we have just shown that if you are able to see or state a certain integral where the derivative or the prime and the integrand are unrelated, seemingly unrelated, or actually, well, should be actually unrelated. If they're unrelated, there is a way to solve it. But the way to solve it is, don't know why that word is randomly down there.
Yes, that's what you do.
Yes. Ultraviolet blue. Ultraviolet blue.
Oh.
Anyway, it's a way of remembering it. Some calc teacher said it once. Wasn't me. Not that smart. Integration by parts says I can take an integral where the prime, the u prime, but it's a v prime. Yeah, I know. Where the prime is seemingly, or in all honesty, actually unrelated to the integrand, and have a way of rewriting it that could possibly lead to a solution. Now, wait a minute. Last night's homework. Didn't we talk about just a second ago the really weird one with a sine squared? Number 49. Is there a rule for sine squared? No. But if you rewrote it with the double angle of cosine, is there a way to integrate it? Yes. Kind of what's going on. But what rule did I just go backwards from? So when you do integration by parts, ultimately you're kind of looking at a product. Not a simple product rule, not by a long shot. But a product rule was somehow involved. Because do you guys see this u times v that's in this solution? Now some of you are like, wait a minute. I see you're redefining an integral in terms of an integral. That's not going to help, but wait. What has happened to u over here in this integral? Remember, we're rewriting and hopefully being able to solve. What has happened to u? He has a d in front of him, and what does d mean in calculus? Derivative, right? The u gets derived. In order, over here in the integral where I'm going to get stuck, the u has been derived, and what has the v? What's happened to the v? He was a derivative, and what is he now? So how do you go from a derivative backwards? And this is the key to integration by parts. Finding someone who can be integrated. So this one must be possible. If it's impossible to integrate something, you better not make him V. Make him V. Wait a minute, we have to figure this out? Whoever you make V in this expression, or I should say dV, must be able to be integrated. So I'm going to actually put a D in front, because V was received by integration, but you started with, oh no, well, okay, technically the dV is what you started with. The dV ends up getting integrated and the U ends up getting derived. Now you can take the derivative of anybody. That's not going to be a problem. Anything that you choose, you can take a derivative of, but you want this to get simpler. Because if you can go from an expression to another expression, yes, I know it'll still be an integral, but if deriving the U made everything easier, well, maybe it'll be possible. Let's take this guy. Let's take this guy. You guys saw that there was an x and a sine x, right? There were two different pieces. The question is, who do we lump together with the dx? Because we know that this stands for some sort of differential, right, guys? We have the dx always, always, always go in with this dv part. We look at an integral in two parts, integration by parts, splitting them up. Somebody needs to go into this derivative category, and somebody needs to go into this on his own category. The dx is going to take someone with him. Who is he going to take? X. Could you integrate x to be x squared over 2? Yes. Could you integrate sine to be negative cosine? Well, stink. Either one could be integrated. Remember, at the very bottom over here on this side? It's fine. What did I say about the two parts? U has to be able to be derived. We want it to get simpler. And dv has to be integrated. We just talked about the x and the sine of x. Either one can be integrated. So choosing dv, I'm not really sure. Let's think about the u instead. Both of them could be integrated. Okay, so fine. What if he was u? What would his du be? Is that simpler? No. What would his du be? His derivative? 1. Is that simpler? What would his derivative be? Is that simpler? Okay, so what if I went ahead and said, if I was choosing my u and my dv, my u, the x derived is simpler. And the dv, well, he's the other dude. At least I can do it. Okay, I did that mental math. Pause. What does ultraviolet voodoo say? This guy is going to end up equaling u times v minus voodoo, v times du minus a negative. Hey, wait a minute. Did the impossible just become possible? What's the integral of cosine? What is the integral of sine of x times x? Negative x cosine of x plus sine of x plus c. You choose u to derive to be simpler and dv, something that can be integrated. Well, either after 1 or 2 or 3 or 10 iterations, eventually you'll get something you can integrate. I know. We'll practice a lot more tomorrow. If you're bored tonight or wanting to start homework, go look up videos of integration by parts. There are plenty of them. Bye.